Hello, everyone, and hello, people of the future. My name is Kevin Perlow, and I am the Technical Intelligence Team Lead at a financial institution. Today, I'm going to be discussing a concept called financial payment standards. So I'm going to be discussing two standards here, the ISO 8583 standard, which is for cards, and the extensions for financial services standard, which is you can think of it as an API for for interacting with hardware on an ATM. I'm going to be discussing how threat actors incorporate these two standards into two pretty specific malware families, FASTCash for ISO 8583 and INJX Pure for extensions for financial services. And in the context of how these malware families work and sort of the inner mechanisms of them, I'm also going to be discussing the advantages and drawbacks that come with integrating these payment standards into a malware family. So jumping right in, the first thing I want to discuss is ISO 8583. Now, ISO 8583, as I said, is a standard for financial card transactions. So anytime that you go to an ATM or anytime you go to a point of sale device at a grocery store to do, say, a self-checkout, all of those are going to create an ISO 8583 message and an ISO 8583 transaction. And what this is a standardized set of fields and a standard structure of fields for transmitting the data from your card and for your transaction over to a payment switch, from that payment switch to a bank, and then on back to approve or reject the transaction that's happening. This is the basis of the FASTCash malware, which is what we're going to talk about in just a few minutes. But first, just an example on the screen, this is very literally an ISO 8583 message, and this is sort of what all the fuss is about. So just breaking this down into a couple of different parts, there are three parts to one of these messages. There's a message type identifier, which you can think of as sort of a file header or message header, and that has some metadata about what type of message something is. There is a bitmap, which will indicate what fields are present in one of these messages, and then there's the data elements, which are those fields. And so the purpose behind items 2 and items 3 there are that there are over 100 different options, such as the primary account number, the transaction date and time, and all sorts of other data that can happen or that can be tied to one of these transactions. And so you don't necessarily want to transmit all of these because most transactions don't use all of these fields. And the bitmap just is there to specify which ones are there for the payment switch to look at. I do need to break down the message type identifier just a little bit further. There are 4 parts to this. So there is a version, which is the first digit. There is a message classification, a message function, and then finally the source of the message. Where did the message originate from, the bank or the ATM or some other entity? So going into the example message that we had on the screen before, if we break this down into a couple of parts, we can see the first 4 digits, as I mentioned, are the message type identifier. And so the first digit of those 4 digits indicates the version, and in this case, this is version 1987 of the ISO 8583 standard. The second digit here is the classification, and this is really important for the FASTCash malware that we're going to be talking about. The classification indicates whether or not something is a financial message, which in this case it's set to 2, so it is, or whether it's a chargeback or an authorization. The third digit indicates whether something is a request or whether it's a response coming back. And then finally, as I mentioned, the fourth part is the source of the message. So breaking this particular example down, and this is just one that I pulled online and made a couple of changes to. The first thing we have is the bitmap, and this one specifies a couple of fields that are present. So we're going to look at the first 3 of the 4 that are specified. Field 2, which is the primary account number, field 7, which is the point of service entry mode, field 7, which is the transaction date and time, and field 22, which is the point of service entry mode. And if you want to decode a bitmap manually, that's a bit too time intensive, but there are some options there on the bottom of the screen for you to take a look at on your own time. Most people, though, just run these through a decoder and they have it tell them, hey, these are the fields that are in a message. So real quick, here you can see data element 2 or field 2, and this is the primary account number. The first 2 digits in this specify how long the primary account number is, and in this case, the first 2 digits are 16. So the next 16 digits are this user's primary account number. And this is just, again, one from an example online. It's, of course, not a real one. Here you can see just a timestamp in UTC. And finally, the point of service entry mode for this transaction. And this one's pretty important for when we get to the Windows FASTCash malware. But this point of service entry mode is set to 011. The first 2 digits in this indicate whether something, or indicate how something was entered into the terminal. So in this case, this is a manual entry, meaning someone typed in the data. But if you look at something where the digits are set to 90, that would indicate a card swipe. And so there are a couple other options in that regard. The last digit in this, or the third digit in the point of service entry mode, indicates whether or not a terminal has PIN capabilities. And of course, most terminals these days do have PIN capabilities, but this way the device doesn't send a message back saying, hey, can you enter your PIN, when there's no PIN to be entered. It's sort of a safeguard against that. So those are the core principles that we need to know for working with the FASTCash malware. Now, what is the FASTCash malware? If you're unfamiliar with this malware family, this belongs to a very specific subset of North Korean threat actors that also engage in Swift heists. Sometimes people use FASTCash to, or they use FASTCash as a term for that threat actor. I wouldn't necessarily recommend that. And sometimes people use this term Lazarus group for just broad North Korean activity. But this malware is tied to a very specific set of activity from North Korean threat actors. There's a very small cluster of tools and techniques that go along with what they do. So what this malware does is it is injected into a payment switch, and it is intended to either fraudulently approve ISO 8583 messages from the attackers sitting at ATMs and allow them to withdraw money, or if the transaction isn't originating from an attacker, it can transparently pass that transaction to and from the bank, and no one would ever know that anything happened. That's the general idea behind this malware family, and we're going to look into the reverse engineering and how this integrates with ISO 8583. There are three types that have been, at this point, all three are actually in public, in the public domain. We're going to look at two of them. We're going to look at the first AAX type, which was the one that USCERT reported back in, I believe, 2018. And we're going to look at the Windows type, which is one that came out, I guess you could say came out or was used last year. Now, all three of these are tailored to the environments that they work in. And the reason for that is that there are slightly different implementations of ISO 8583 depending on your own architecture and depending on the payment provider that you use. So whether you use Visa or MasterCard or Star or something along those lines, there are going to be some different implementations or interpretations of the standard. So jumping right into the reverse engineering for AAX type 1, if you were to open the USCERT report and then you were to open the sample yourself in IDA, you're going to see just a few small differences. One of them is that the strings that I guess you could say should be there won't be there in your sample. And so this first slide here is just to kind of give you some tips on how you can go and collect those strings. You can probably write a script for it, but I personally just did it manually. You can go into this section of hex, look at the offset that it specifies, and what you get is just a pointer to the string that you're supposed to be working with. So this one is actually a debugging message, and there are a lot of these. There are a lot of debugging and logging messages within this malware to help the threat actors operate, because what they're doing is fairly complex. But we don't need to worry too much about that. For the purposes of this talk, I've got all of the strings labeled. What is significantly more interesting is the strings and the interaction for how some of the functions that are built into the malware are called. So on this slide, you can see a couple of different function calls, and these are pre-named within the malware. There is get field string and set field string on this slide. There are a few others, like copy field string. All of those are related to interacting with an ISO 8583 message. And so the important reverse engineering concept that you need when you're looking at one of these is to understand that there is a pattern for how these work. So before set field string is called, for example, there is a load into register 3 for a digit, and that digit is going to be the field that is manipulated. And above that, there's a load into another register for a string, and that's actually the data that's going to go into that field. So as long as you know that pattern, you can really do the reverse engineering for all of this. And get field string is very similar. There's a load for the fields that is going to be retrieved. But in this case, since it's not setting any data, there's no data load. Once you have all of those principles kind of in mind, you can go through and map out how this malware works. And so the way you would read this graph here is from left to right and top to bottom. So you can think of this as, again, this malware is injected into the payment switch, into software on the payment switch rather. And a new ISO 8583 message comes in, and this will intercept that message and call this function new read. From there, it will call check sock, and check sock will call get IP, INET address, and it will perform a check for a valid IP to make sure that the message is originating from where it's supposed to be. And then it will move on sequentially down the line to check for flags and then read receive and so on and so forth. We're not going to go into every single one of these. We're going to go into some of the important ones for this payment standard. So again, the first thing here is a check sock function, and I have on the left side of the screen I guess you could call it like the overhead for the new read function. When check sock is called, it performs an IP address whitelisting check. It wants to make sure that the transaction is coming from a valid internal IP address. There's nothing too much to worry about there. But as we kind of move along, and on the left again on the screen, you can see how we're progressing sort of through this code. Once it does the whitelisting check, it's going to retrieve a bunch of information from a couple of different fields. So the fields that it's mainly interested in at first are the message type identifier, the primary account number, the processing code, and then it also pulls the advice reason code. And depending on what data that it sees there, it has two options. It can either transparently pass this message on to the bank because the primary account number didn't line up with a whitelist that the threat actor set up, for example, or some of the fields that were supposed to be there weren't there. And if any of those things are the case, it will send that on to the bank, and it will be as though nothing ever happened. The bank will send a proper response, and that response will go back to the ATM. On the other hand, if it does see data that it's interested in, and we'll dive into the mechanics of that a little bit more in the Windows one, it can generate one of three types of responses. So here there are generate response transaction 1 and response transaction 2. And there is also a response inquiry, and I'll dive into those in just a second as well. But depending on this fraudulent response that it generates and sends back to the ATMs, it will, assuming all of that works, it will log that it's blocked that message, and it will send that response back, and then the process will repeat. So diving into transaction type 1, and transaction type 2 is actually very similar to transaction type 1. The malware will intercept the ISO 8583 message. It's going to, again, pull those fields that I had mentioned, but then it's also going to copy, it'll dive into this, and it'll copy a bunch of data from the original ISO 8583 message. There are some different fields here, and I've got a full list on the next slide. All of the data that it copies, it's used to construct the message that's going to go back to these ATMs. And part of that is because the ATMs probably, although we don't know for sure, but we can make an assessment that the ATMs probably expect to receive data in a certain way. Again, this is all environment-specific stuff, so we have to make some inferences about what the threat actor is doing. So with that in mind, the fields that it's going to copy are the primary account number, processing code, and so on and so forth. There's a long list of these things here. And then for transaction type 2, it's the same list, but minus a couple of track 2 fields. Now, once it does that, it reconstructs the message and sends that back. It's going to generate a random balance for a random transaction amount as part of this process, and then the ATM will allow the threat actor to withdraw cash. So the other type of response that it can make here is the inquiry response. So this is a response to a balance inquiry. If you walk up to an ATM and you put your card in and you say, hey, how much money do I have? This is actually the type of transaction that would come back. Now, I think the threat actors probably set something like this up to allow them to test their malware. I can't really think of any other reason for doing something like this, but it would be very obvious to a threat actor if this were working properly with the balance inquiry, and you'll see why in just a second. So inside of the balance inquiry, it copies fields in a very similar way to that transaction amount, but there's also this format string, which I have as kind of the multicolored thing on the top right there. So this format string is very important. It's for determining how, or it's for the structure of information that's going to go back into field 54, which is the field that handles all of your account balances. And so breaking this format string down just a little bit, we have two kind of non-important items and then one very important item. So the non-important ones here, it will say that the amount type is set to 0, which indicates that the amount going back is something called a ledger balance. For the purposes of this malware, not too important. We'll see an available balance a little bit later on. But the main thing here is the currency code. And so this currency code is set to 356, which is the Indian rupee. And what you can infer from something like that is that for whatever reason, the ATMs on the receiving end of this expect to receive data in that denomination. And so you can make some assumptions and do some open source research. And I can't really go into victimology in a talk like this, but it will make it pretty clear as to why this might be the case and why or who this victim probably was. So once those are set, there's also a randomized amount of currency that goes along with this, and that gets sent back to the ATMs as well as a fraudulent balance inquiry response. So putting all of that together, we have injected the malware into the software on a payment switch. We have done some preliminary checks anytime an ISO 8583 message comes in to see if it's one that we're interested in. If it is one that we're interested in, we've taken some decision points and we've either passed the transaction on, or we have blocked the transaction and sent a fraudulent response, either a fraudulent withdrawal or a fraudulent balance inquiry. Now, again, I don't have time to go into type 2 of the AIX malware, but this graph is here in case you want to reverse engineer it on your own time. If you can reverse the first one, you can reverse the second one. The concepts are the same. There are just some structural differences. And this AIX type 2 is sort of a bridge to the Windows one. And so from a high-level perspective, you can, if you were to look at this graph, you would see that a lot of the payment logic has been consolidated. And so that's really what we're going to look at for the Windows version as well, is how they consolidated and sort of changed this payment logic. So within the Windows version, we have, once all of that same stuff happens, a whitelist. They've added a blacklisting function in, but it's done the IP address check. It's done all of these decision points. It is going to go into what I call the generate response parent. It's sort of a new function that was added into this malware. So the response parent is responsible for taking in some additional data and doing some additional checks before proceeding with whether or not to generate a fraudulent response. The response parent has two checks. The first check is that it is going to look for field 0, the MTI, and it's going to check whether or not field 0's third and fourth digit are set to 00. If we think back to our original example, we had a financial message that was 0200, and that indicated that something was a financial request. So here it's looking to see if something was also 0200 or 0100 to indicate, hey, that's also a request, as opposed to if it were 0210, which would indicate that something was a financial response. The malware doesn't want to intercept a financial response because it wants to just pass that back on to the device that's expecting that response. So that's the first check. The second check is for the point of service entry mode. Now, the point of service entry mode, again, if you think back to that example, it's how the data was entered into a terminal. And here it's checking that the data in the point of service entry mode field starts with a 9, which indicates that this was a card transaction rather than manually entering it. And that's just an operational expectation from the threat actor that there aren't people here just manually entering in a whole bunch of data. So assuming those checks pass, it will jump into a response workflow. And there's a little bit of redundancy here, but this will again grab the MTI, and then it's going to grab a whole bunch of fields that you can see here on the screen. And the first check here is to just see, do these fields have data in them? And one of these is field 3, which is used in just a second as well. But for the most part, that's all this check is concerned with initially. And if these fields don't have data in them, the malware can't or doesn't expect to be able to process this properly, and so it's going to exit this workflow. Now, assuming all those checks are met, the next set of logic here is for looking at that processing code, which is in field 3. If the processing code starts with a 3, that's going to indicate that this is a balance inquiry, and we'll see a workflow like we looked at before and that we'll look at again. If it starts with a 0, it's going to indicate that it needs to do a fraudulent transaction response. And then finally, if it's none of those things, it's going to return an invalid PIN response to the user. So I have here all three options kind of on the screen, and this is how they look in IDA if you were to screenshot it out. And we see that format string show up again. I know it's a little bit hard to see on the graphics, so I've kind of put it in multicolor again on this next screen. But we have, as part of our balance inquiry response, instead of the Indian rupee, we have changed the currency to Turkey's currency. And that's pretty important. Again, this would indicate that for whatever reason, and most likely it would be tied to victimology, that for whatever reason the malware expects, or the malware expects to interact with an ATM that in turn expects the currency to be turkeys. And so that's a pretty important threat intelligence factoid there that you can pull out of something like this. And it kind of gives you an idea of how this can be a little bit more victim specific than just something that works everywhere. And again, I have the other two options here for one of those responses. So that essentially is the FASTCash malware. Next, I'm going to kind of jump into extensions for financial services. But while I do that, I would consider these 3 points as sort of a frame of reference for comparison. So the first point is that a lot of things need to go right when you're working with malware like this. It's pretty challenging to interact with all of these devices at that level and to interact with all of these protocols. And so when you're doing that, a lot can go wrong. And that's why the malware has a whole bunch of logging information inside of it to help the threat actors out. I think those are the two main things. The other thing is that there are some pretty heavy operational requirements that you need to set up. You need programmers that can do this and can make these changes on the fly. You also need a network of money mules, basically people that are there to withdraw the cash from the ATMs. And so if you're a North Korean threat actor, not the easiest thing to set up. And then finally, you need access to this network, and you need to get pretty far into the network in order to get access to that payment switch and to take a stab at this. So it's pretty challenging, but it does allow the threat actors to operate the ATMs without putting anything on the ATMs and to do these cash outs. So with that in mind, the next thing I want to talk about is something called extensions for financial services. You can think of this as a standardized API for how software vendors are supposed to write their software for interacting with an ATM. So any ATM you go to is able to withdraw cash. It's able to, you can actually deposit cash there. It has all these blinking lights. All of those things go into the extensions for financial services standard. And we're actually going to be looking at one called JXFS, which is Java Extensions for Financial Services. Now, we're going to be looking at this in the context of a specific family, but if you're interested more in traditional XFS malware, there are some links that I have here, and there are a couple of common API calls. None of these actually appear in this particular family, but they are ones that you'll see fairly often within other ATM malware that's out there. But we're interested in this malware family called INJX Pure. Now, I can't go too much into the incident in which this malware was used, but this is an ATM malware family that relies on both XFS and a proprietary ATM implementation. The reason I want to go into this is less to talk about how the malware dispenses cash, because I think that's been kind of done to death in open source and it's not super interesting. What I want to talk about instead is what people can do to an ATM once they get this level of access. And so that's really the context that we're going to be looking at this malware in, or kind of the frame of mind we should have. And we'll see some pretty interesting capabilities there that aren't necessarily built into this malware, but could have been. So with INJX Pure, the operators can do some pretty traditional, or they can perform some pretty traditional actions. Of course, it's ATM malware, so they can dispense cash. They can query device information, and that's really used to kind of find out how much cash is in the ATM. And they can execute arbitrary code. All of those things are pretty common to any ATM malware family, and honestly, aside from dispensing cash, they're common to any malware family just in general. But we're going to focus, we're going to dial in on the cash dispensing function and the XFS components that follow that. If you are interested in a full reverse engineering of it, it's been kind of done to death in open source, and so here are three just references for that. The third one we are actually going to reference again, and that one's a very good one, and so we'll come back to that. But the important thing that you need to know about this malware is that the threat actors essentially deployed this malware to a bunch of ATMs, and the malware, when it runs, it creates an HTTP server, and that server can accept GET and POST requests that carry out those commands that I mentioned before. And that's really the core concept. There are two workflows to kind of get you to this spot from the malware's viewpoint. The one we're going to be looking at is the one that is just directly responsible for all of the different commands. So we're going to dial in on the dispensing commands, but the other ones are up there. This sits within the server that's created, and I have that here on the screen. Basically, it opens a listener on a high port and just listens for those requests. So within this dispensing commands, there are two possible branches that the malware can take. It can query, I call it querying the device information, but it's really querying the cassette information, and it can dispense cash. And so dialing in just on the first one, the query, we can see a couple of different XFS callouts here. So we have get cache unit, we have a dispenser call, and we have get number of cache units. So these are things where if you're looking at the code, these are not standard Java calls, whereas pretty much everything else is. And they're not standard JavaScript calls, and again, pretty much everything else is in that regard as well. So these look like they could be XFS implementations. So how do we figure that out? Well, if we take get cache unit and we throw it into the magic Google box, you will get this Google book. It's some sort of ATM book. I think it's in German. It's from like 2004. And you can see here that call to get cache unit within this JXFS implementation within this book will return this .cache unit. Not super illuminating if you're trying to figure out what this is doing, but it at least indicates that this is probably, we're probably on the right path to determining that this is XFS. So the next stop, and probably the better stop once you know about it, is to go to the actual documentation. And so if you go to the send documentation and you look at book 5, which holds all of the different, I guess, API calls for this malware, or sorry, for XFS. If you go in there and you look for get cache unit, you will indeed see an entry in the official documentation for get cache unit. And this, with a little bit more research, this essentially returns the information about the money that is stored in the ATM in different cassettes. And there are some differences between how this is written out here and how the malware, how the malware uses it and how the proprietary ATM software uses it. But essentially, you could call this an XFS implementation, and I would be comfortable saying that the developers for the ATM probably just built their implementation on top of XFS rather than in place of XFS. So that handles one of the API calls. But what about get number of cache units? I've got to give a huge shout out to Frank Baldwin, who did a presentation last year, more specifically on how this malware works and the context in which it was used. But one of the things he discovered was that the ATM software, as part of the incident response, was actually uploaded to VirusTotal. So I'm not going to just paste all of the vendor's code, all over the place on here, but I'm going to show the relevant things. So get cache unit sits within this ATM's code for peripheral, under the context of peripheral.notesDeposit.get cache unit, and the same goes for get number of cache units. And what I want to talk about here is less about what these are doing, and more about what the threat actors could have done. So under that peripheral.notesDeposit call are a bunch of other fairly mundane calls in terms of interacting with the ATM, but they would allow the threat actors to query a lot of these types of information. So most of these aren't super exciting. There's some extra calls for retrieving more information about the cache units, if you haven't heard enough about the cache units. You can get the media status, you can get some other settings. Nothing too groundbreaking, but it does give the threat actors a little bit more information. So the next step here, if you're interested in threat actor capabilities on an ATM, is to actually back that up as like one notch. And instead of looking at peripherals.notesDeposit, you would look on the ATM software for just what the peripherals did. And again, this is something the threat actors had access to. So looking at just the peripheral class, instead of notesDeposit, there are some other options. You can call peripherals.screen and peripherals.host, .systemservice, and .pinpad. And under each of those are some actions that you can take. The most important ones, I think, are this idea of disabling and enabling keys. Why might a threat actor want to do something like that? Well, if you're trying to coordinate a cache out, what you might want to do is maximize the amount of cache that is actually sitting in an ATM. And if you just let people use the ATM all day, you might be sending a money mule to an ATM to pick out cache, or to pick up cache rather, and there might be none in there, or there might not be as much in there as it could be. So this creates an option for threat actors to perhaps disable and enable keys on an ATM to stop it from functioning the way it's supposed to, so that other people try and use it and have to walk away from it. That is sort of a high variance strategy, because if you have an ATM that's not working, you raise the risk that someone's going to go look at it. But depending on how you're timing this, if you do that, say, late at night, or earlier in the morning, those are some options that a threat actor could take if they're willing to kind of roll the dice a little bit on how much money they're taking out. There are some other things that I haven't listed here. They're a bit more mundane. One is the blinking lights on an ATM. You can make those blink all you want, but from a security standpoint, go for it. We're more worried about people taking the money out, I think. But those, I think that really speaks to the capabilities that a threat actor has there. So kind of just circling back on, or kind of closing the loop on the rest of this, we have one other part of the dispense function, which is just the actual dispensing of cash. And so dispense itself is possibly an XFS implementation. I can find it in the documentation, but it's implemented significantly differently, I think, within the proprietary code that's available. So it's a little bit unclear if this one is built on top of XFS or built in place of XFS. But again, it speaks to the threat actor capabilities when they're interacting with a device like this. And so that is really what I wanted to talk about from the extensions for financial services approach. So if we think about the FASTCash malware and we think about this kind of in the same context, in FASTCash, we were able to send people to an ATM and they would run a card into it. And as long as it's one of the threat actor's cards, it would fraudulently approve a transaction. Here, we have a threat actor who developed proprietary malware. The way this works is they would have sent people to those ATMs at a specified time to have the cash come out of an ATM and via post request, and then they would withdraw that cash themselves. And so that's sort of the comparison approach there. One of the problems here is there's some increased development time because they had to develop malware specific for this ATM. And they also have to work with some proprietary implementations when they did that. That might not necessarily be documented. So that's a little bit challenging, and testing is always a little bit challenging. And so those are some of the things that kind of come up there. But ultimately, they did have the opportunity to run an attack like this. And so with that, I will teleport myself back to the future and back to another room. And I'll have just this slide up there if you want to see some concluding thoughts. But at this point, thank you for listening to my talk. And I'm happy to take as many questions as I can.
All right. So first of all, thank you all. There are two things I want to just mention before I go into a couple of the questions that came up during the talk. The first is there is a slight error on one of the slides, which is data element 60. I have listed as being the advice reason code. That is the advice reason code for certain payment switches, but not all of them. That's actually a private reserve field. That is corrected in the slides that are going to be uploaded. The second thing I would mention is that there's a white paper that covers a little bit more on AAX type 2 and also has some additional context and tooling listed. So feel free to check that out when that goes up online tonight. There are a couple of questions that came in, and we're on about 45-second delay here. So if you hear me say this and you have a question, it means you should type it. One of the questions that came up is, can I elaborate on what a payment switch is? So that's a great question. I probably could have done a little bit of a better job on that. A payment switch is a device that sits in between all of the payment devices and a bank that needs to approve transactions. So you've got ATMs and you've got your grocery store point of sale devices, and this payment switch will process all of the messages coming into those and decide whether or not to forward those on to a bank. And then when the bank decides whether or not it wants to approve or disapprove a transaction request, it'll send that to the payment switch, and the payment switch will send it out. It's a way of just processing all of the different types of data that are coming in. And so that's why it's so important to the ecosystem. So another good question that came up was, well, should we just change the ISO 8583 standard? I would never recommend that, and it would also be impossible even if I thought that were a good idea. But the ISO 8583 standard is the card payment standard for absolutely everything. There are some things that go along with card payments, such as like EMV transactions, for example, and that was something I thought someone might ask, and I think this is kind of related to it. There are different ways to do these card transactions that could randomize the data. But ultimately, and by randomize the data, I mean they might make it less predictable for what's supposed to be going back to an ATM. So those things might make it harder to do these types of attacks. But ultimately, what's happening here is that the payment switch is compromised, and there's nothing wrong at all with the payment standard being used. The ATMs are working the way they're supposed to be, in a very real sense. They're processing these messages. So that rolls into the next thing, which was, I think Kat was the one that asked, how do you even detect an attack like this? I don't give official recommendations, but I touch on this a little bit in the white paper. All of the mechanisms for getting to this point where your payment switch is compromised, all of those are or almost all of the tooling used by this threat actor, the FASTCash threat actor specifically, involves PowerShell, it involves scheduled tasks or created services. And those are all pretty standard things that you can and should be looking for in your enterprise. So if you've got that kind of endpoint detection, then it just becomes a question of identifying those anomalies and having the right analysts and having those analysts do the right analysis on all of those things. So by the time it gets to the payment switch and this cash out happens, you'll detect it because the money will, all your ATMs will be empty all of a sudden. And so the idea is to stop it before it gets to that point. I'm probably not supposed to say it's too late, but it is basically too late at that stage. Now, I have another question here from Sean, which is how does INJX Pure actually get onto a payment switch or the ATM? So INJX Pure doesn't get onto a payment switch, and I think that's good to touch on too. INJX Pure is different adversaries method. So this is a Latin America adversary. I can't really talk about the context for a couple different reasons, but they deployed the malware directly onto the ATMs. I don't think I can really disclose how they did that, but I can tell you that that's not a novel, like a bulk ATM malware deployment is not necessarily a novel technique. So thinking about one that's in open source, if you can read Korean, a couple of years ago, there was one in South Korea where there was an issue where they used, I think, the antivirus management tool to deploy malware to a bunch of ATMs. So I'm not going to comment on whether or not that's what happened here, but that's the type of attack you're looking at to get that there. Now, what that means, though, and the difference between these two attacks is that someone's got to be there to pick up that cash that's getting automatically dispensed. And if you go on Twitter, you can see some examples of where someone wasn't there and cash just got spat out onto the ground. So wanted to touch on that and clarify that. And no, that question wasn't too late. I think that there's one other thing I did want to talk about here, which is the question of, so we've got all this technical intelligence, and I've got kind of a minute or two to touch on this. How does all of this fit into a threat intelligence picture? So it's not enough to just track that there are all these technical characteristics of this malware and to understand how it works. You certainly need to do that, but you also need, if you're in this industry, to be doing really good collection with other peer financial institutions, because this data is rare and these attacks are rare, but they're so impactful. So that will help you build an operational picture out of it, and it will also help you build a strategic intelligence picture in terms of starting to make business decisions or starting to make security level decisions at a bigger scale on these types of topics. And with that, I think we have run through questions, and I think we are about out of time. So I just want to say thanks again for everyone for tuning into this. I know it's tough to sit through a lot of webcasts, but it really means a lot to me, and I really appreciate it. So thank you.